In 6.1 number 25, they've drawn us this graph right here, and they've given us two equations, both of which are solved for x in terms of y. Now that, coupled with the fact that the graph we have is kind of situated in the way it is, tells me pretty much straight away that this is a horizontally simple region and that we're most likely going to do this integral with respect to y. So what they're telling us to do here is to match the equations with the curves that we're given and then go ahead and compute the area. So first thing we got to figure out is which one of those curves is which. That's going to help us determine how we set up our integral in terms of right curve minus left curve. So we could go to the calculator and play with this just a little bit, but the one thing I think is interesting here is that we've got, let's see, an x-intercept here and an x-intercept right here on those two curves, and I think those should be relatively easy to find. Remember that at every x-intercept, there's obviously an x-coordinate, but then your y-coordinate is going to equal 0. So if I look at this first curve here, guys, which I'm going to bring right down here, it would be x equals, and then if we just put zeros in for the y's, those first two terms are both going to become 0, and we end up with x equals 10. So one of those curves has the x-intercept 10, 0. And the other one, this one right over here, again, I want to know what x is going to be when y is 0. Well, making both of those y coordinates 0, we just end up with x equals 40. So what I think that tells me here, guys, is that, let me take a look at this one right here. The first one, the one in blue right there, oops, I lost that right there. That was a 10, 0. Okay, that's the ordered pair right here that's further to the left, 10, 0. And then this one is further to the right, 40, 0. Okay, so what does that tell us, guys? That this curve right here is actually the blue curve, the one that has an x-intercept of 10. I'm going to call that x1. All right. And then what that tells me is that it's the red curve on the right that ends up being this curve right here with an x-intercept of 40. That one goes right there, and I'm going to call that x2. You'll see why I'm labeling those something different here in just a second. Now, the one thing that they did for us that was nice here, guys, well, in addition to giving us the graphs, it looks pretty clear that they've told us here that the point of intersection between the blue curve and the red curve here on top has a y-coordinate of 3. Then again, right here, the second point of intersection looks like it has a y-coordinate of -1, and this lowest point of intersection has a y-coordinate of -5. That's all good to know. Now, what we're dealing with, though, here, guys, is kind of a complicated problem because there are two regions here. I like to read this from bottom to top. So I'm going to call that region 1 and then this region 2, that if we want to find the total area between these two curves, we're going to need to come up with the area of each of those regions and add them together. But what's interesting about this is that the boundaries change. Let me show you what I mean here. So our total area, I'm simply going to write as area 1 plus area 2. Area 1 being this lower region and area 2 being the upper one. Okay, so in area 1, that's going to be a definite integral now. And again, we said we're doing all of this with respect to y. And when we're doing horizontal rectangles, something that looks like this, we always want to read it as right curve minus left curve. Now, in that little red rectangle that I just drew, it's the blue curve that stops that rectangle on the right. And the blue curve we had called x1. So since somewhere on my paper I've already labeled here what x1 is, I'm just going to leave it like that. x1 minus x2. x2 being the red curve, and that's what stops that rectangle on the left. So that's my integrand, guys. x1 minus x2, we're doing all of that with respect to y, and the limits of integration need to be the lowest and highest y values in this region. Looks like we begin this thing down here when y is -5, and we end it right there when y is -1. Now remember, we're integrating with respect to y, so all of these variables need to be y's as well. Well, x and 1 right here, guys, are functions that are expressed in terms of y. So when I go to put that in my calculator in a minute, that should work out okay. Okay, we're going to add to that now a second integral, now for region 2. And when we get to region 2, it's the red curve now that stops region 2 on the right and the blue curve that borders it on the left. So this integrand is now going to have x2 guess I'm doing subscripts there. On the right, minus x1 on the left. Integrating again with respect to y, and our lower limit of integration for region 2 is -1, and the upper limit is right up there at 3. So that's what we've got going on here, guys, and this is going to get a little bit messy when we go to put all this in the calculator. I wonder if defining it wouldn't help. Nah, I don't know that I'm going to run with that. So, okay, let's go ahead now. This is going to involve a lot of bouncing back and forth here because I don't think I have this thing open in front of me here, do I? Okay, let's see what I can do. Okay, so, whoop, that's not what I wanted. Calculator, here we go. So we need a definite integral here, guys. So I don't think I knew. I just had an integral button right there. I just noticed that. Okay, our first integral we said we were going to set up was going to go from -5 on the lower limit of integration up to, here we go, -1 as the upper limit of integration. And in terms of the integrand, all right, let's see what we had here, guys. It was x1 minus x2. So it's the y cubed curve that I have to type in first. Okay, so let me use some parentheses to help me keep this straight here. So that is going to be a y to the third power. Got it. And then what? Minus a 26y, and then followed by a plus 10. So there's the first curve right there. Let's close it off. And then minus the second curve, which is going to be 40 minus a 6y squared, got it, and then a minus y to the third power at the end of all that. Okay, and we're integrating all of that with respect to y. So I'm tempted here to do the second one at the same time, but I think I'm going to go ahead and hit enter. I wanted to make sure that I got a positive answer for the area of that region there, and that might have gotten muddied a little bit if I did the second integral at the same time. Okay, that's where we're starting now, and now we're going to add to that, let's see, a second integral, this one beginning at -1 and ending up at y equals 3. And now we're reversing the order of our integrand here. So parentheses, and now I'm going to begin with a 40 and a minus 6. That was a y squared. And then a minus y to the third power. Okay, let's get out of there. Gotcha. And then minus, my parentheses didn't look great up above. All right, here we go. And now we're going to begin this part now with a y to the third power, and then a minus 26y, and a plus 10. Okay, right arrow a couple times, again, integrating everything with respect to y. Now, I don't know, as I was looking at that graph right there, assuming it's drawn to scale, those two regions look like they're similarly sized. So I'm thinking I should get an answer here somewhere in the neighborhood of 128. Okay, that was weird. And I got exactly 128. All right, interesting. So what I think I now know here, guys, we'll see if I'm right, is that the area of that first region was 128, and we need to add a 128 to that as well, which should get us a whopping total of 256 square units for the area of the entire region. I'm looking at the solutions manual in front of me, and yep, that answer right there is 256. Now, if you were wondering, would it have been possible to do all that at once? If we had done that, we would have run into trouble, and it's because of the changing boundaries. This is actually going to feel a little bit like a displacement problem here. If I went back and tried to do everything at once, going from -5 for my lower limit of integration all the way up to +3, I'm pretty sure this is going to give me an answer of 0. Ooh, it gave me -3.2 times 10 to the -13th power. That's your calculator's way of saying, yeah, it's really, really close to 0. And the reason it did that, guys, is because it treated one of those 128s as a negative because the borders changed. Now, the other thing we could have done that would have been cheating a little bit is I could have actually done this with one whole integral, but to account for the changing boundaries, to say I don't really care which function is on the left and which one is on the right, I could have typed in an absolute, no, not like that. Okay, I could have typed in an absolute value here. So what if I had tried, okay, let's see here, here we go. I might have been able to type in an ABS, and then started a parenthesis right there and ended it right there. Yeah, and if I did that in one step, doing an absolute value around the entire integrand, then changing boundaries don't matter. We know that the regions can't have a negative width, and it would have gotten me the right answer in one step right there, which was 256. That said, I think I learned a little bit more doing it step by step, and we ended up with 256 for the answer we were looking for problem number 25.